All right, so in this lesson, lesson 3.7, we're going to talk about average atomic mass. So your goal is twofold. One, be able to define average atomic mass, and secondly, to calculate average atomic mass. Right? So the formal definition of average atomic mass is the weighted average, meaning that it depends on the amount that exists of all the isotopes or different versions of the same element. So if you recall in fusion, we were saying that in order to create new elements, elements crash in order to form a larger element. And sometimes we end up with elements that have a different weight or a different mass. So for example, Ag, there's two isotopes or two types of Ag. So Ag is the symbol of silver. You can have silver that has a mass of 107, or some silver atoms have a mass of 109, right? And if you take the average of both of them, this is how we get the number 107.87. And it's dependent on how many silver atoms that weigh 107 versus how many silver atoms that weigh 109. So let me talk about what a weighted average means by giving you a visual example. All right, so let's say we have hydrogen. And for hydrogen, there are two types of hydrogen. There's hydrogen 1 that will be shown as purple circles. Right, so let's say we have 50 hydrogen atoms in a jar. Right, so just imagine that you can see the hydrogen atoms in this jar. And let's say we have 50 atoms of hydrogen that have a mass or weigh 2. Right, and this will be shown in green. So notice that if I have 50 purple hydrogens and 50 green hydrogens, right, their mass is exactly in between. So their average atomic mass is right in between both of them, which makes sense, right? I have the same amount of purple as I do with green. But what if I had more purple hydrogens or more hydrogens that weighed a mass of 1? What do you think will happen to this average atomic mass? Well, let's see. So if I continually add more than 50 purple hydrogen ones, you'll notice here that our average atomic mass shifts closer to hydrogen 1, right? So the more of one version there is than the other, the closer your average atomic mass moves to that one. So this is the purple end, right? So the more purple I have, the more the mass will be closer to the purple ones, right? What if the opposite happened? So what if I had lots of green hydrogen 2s, but not a lot of purple hydrogen 1s? Well, then if you notice the mass again here for the average atomic mass, it's going to shift closer to hydrogen 2, the green hydrogen 2, right? So depending on which one there's more of in our universe, in our world, right, the average atomic mass will move closer in that direction, right? So that's what it means by a weighted average. The more of that thing you have, the closer the average atomic mass will be closer to that element or that isotope, right? But how do we calculate average atomic mass? Let's do a practice problem. So let's say that there are two isotopes of boron, which is true. We have boron 10 and boron 11, right? So for boron 10, there's about 19.9% abundance. So meaning if I took a jar and I put a whole bunch of boron atoms in there, about 19.9% of the borons will have a mass of 10, right? And if I took all the kinds of boron and put them in a jar, about 80% of them will have a mass of 11, as shown in this green. So most of them weigh about boron 11. So if most of them have a mass of boron 11, or the green one, you could probably guess that your average atomic mass will be closer to the number 11 rather than 10, right? Because as we saw earlier with this, the more I have of one type, the closer the mass will be to that type. It's a quick and easy way to check and predict what your answer should be before you even start doing math. So we already know that whatever number I get when I calculate average atomic mass, it should be closer to 11, right? Because this is the mass and there's more of this boron 11. So to calculate average atomic mass, you need to know two things. One, you need to know the mass of each type of isotope, and you need to know the percent abundance. Right, so hopefully I can color code everything so it's very clear. Right, so starting out with average atomic mass, our mass of isotope A. So let's make this first isotope A, 10. Right, it's going to be 10 times the percent abundance of A. So percent abundance is just the amounts that I have. Right, so percent abundance for boron 10 is 19.9%. 19.9%. Should put this in parentheses, plus the mass of isotope B. So our next isotope is boron 11. And recall from the previous lesson that this number is the mass number. So 11 times percent abundance of B, right? So percent abundance of B is going to be boron 11, so that's going to be 80.1% times 80.1%. Right, so each time I'm taking the mass times the percent plus the mass of the second isotope times the percent. And if you had a third or a fourth isotope, you would just keep this going, right? So then it's going to be plus the mass of isotope C times the percent abundance of isotope C, so on and so forth. But since we only have two isotopes, we can pause here. And let's do the math for these two before we continue on. All right, so let me pull up my calculator. So it's going to be 10 times 19.9, close parentheses, plus, open parentheses, 11 times 80.1, close parentheses. So that will give me 1080.1. Right, so I type all of this into my calculator. Whoops. (1080.1), and the last part is to divide the whole thing by 100. Right, so just to show you that, you might be able to figure that out in your head. Divided by 100 equals 10.8. Right, so I have 10.801. Feel free to round to the tenths place if you would like. Right, so this is going to be my average atomic mass. And if I check my answer, I can check in two ways. One, remember we said that the higher the percentage, the closer it will be to that isotope's mass. So 80% of the isotopes are boron 11, so this one's the most. So this number should be close to 11, and it is, right? At 10.8, if I round it to the nearest whole number, it's going to be 11. Another way I can check is by looking at my periodic table. So for the problems that I give you, if it's a known element, I try to match it to the actual percent abundance. So if you check your periodic table for boron, elements B, so looking for it going left to right straight across, H, He, Li, Be, B. Here it is. It is 10.81. So if I double check here, 10.8, that's pretty close to the actual average atomic mass on the periodic table. So those are two quick ways to check, right? So this is how you essentially calculate average atomic mass.